So I think this all began a couple of months ago. John had reached out to us about potentially hosting a operation session for one of the Mars rover in our new auditorium. He was kind enough to have some of us out there to kind of see one of them. It's actually really interesting. I think a lot of people in here were fascinated with NASA as a youth, and the little 12-year-old boy in me found it really interesting. It's very accessible to the layperson. I'm obviously not a rocket engineer, so the hope is once the auditorium's open, some of the team will come out here and present, and we'll be able to see what goes into planning a day's activity in the rover. Kind of leading up to that, John was also interested in coming out and giving a tech talk, as it were. I also have a little bit about John's background. He's been project manager for the NASA's Mars Exploration Rover project since March 2006. Previously, as science manager and then as deputy project manager, he has helped lead the rover project since 2000. John grew up near Boston. He received his bachelor's degree in engineering from Tufts University in '81 and his master's and PhD in physics from Brown University in '83 and '87, respectively. He joined JPL to work on advanced spacecraft propulsion, which included such futuristic concepts as electric, nuclear, and antimatter propulsion. In '89, he began work supporting the exploration of Mars with the Mars Observer mission and has since worked on 7 Mars missions. Pretty impressive. In addition to his Mars works, John is involved in the development of instrumentation for astrophysics and planetary science and teaches mathematics at Pasadena City College as an adjunct faculty member. Please welcome John.
Thank you. Thank you very much. It's a pleasure to be here. What I hope to share with you today is this tremendous revolution that's going on in our world of exploration, and I think it's appropriate because Google is also engaged in a great revolution of how we do things here on the surface of the Earth and beyond. So let me begin by talking about the first Copernican revolution. For much of human history, this is how we thought of the universe, that the Earth was the center of things, and things like the Moon, Mercury, and Venus, and even the Sun, here, the third one out, all revolved around us, that we thought we were the center of things. And actually, the observational information supported this because, apples fell down to the Earth. The thinking was that everything is sort of just gravitating towards the Earth itself, and so why not have bodies in orbit around us? But Copernicus, and then later supported by the analysis and observations performed by Galileo, said that no, we're not the center of the universe. We're just one of the minor planets orbiting the sun, and that the sun is the center of our solar system. Well, this was heretical. The Catholic Church put Galileo under house arrest for several hundred years. It wasn't until the 1990s that the Catholic Church got around to absolving Galileo from house arrest. But the whole idea was that if we were not the center of things, then what's special about us? That for all this time we thought that we were the center of the universe. Well, since the time of Copernicus and Galileo, we have clung to the notion, okay, we're not the center of things, but maybe we're the only place where there's life. And that has been sort of the anchor of our own arrogance, the arrogance of our species, that we're somehow special in the universe. So the second Copernican revolution is that even that concept is being challenged, and we are no longer the center of the universe, and we are no longer special in that way. So I want to talk a little bit more about the universe, and so if we look at this, oh, I'm sorry, that's upside down. Let me fix that. There we go. Now it's right up. Most of the universe is this. Over 70% of the universe is what they call dark energy, and we still don't know what dark energy is. And then another 24% of the universe is dark matter, and we still don't know what that is. So the stuff that makes up you and me, baryonic matter, protons, corresponds to about 4.5% of the total mass energy of the universe. And even of that, only about 0.5% of that is in the form of stars. So we really can say we only have an idea of about, 4 or 5% of the universe. I mean, if you only know 4 or 5% about anything, well, in school, that's an F. So we really do have a very limited understanding of our universe. So the stuff that we're particularly interested in is this stuff. This is the Hubble Ultra Deep Field Survey. So this is like holding out, a a small p at arm's length at the sky. So it's only about 1/10,000,000th of the total sky is captured in this image. And in this image, you look at it and you go, wow, there's a lot of stuff here. But actually, in this image, very few of these things are stars. Let's see. That's a star. That's a star. That's a star. And there's one more. And I never can even find it. Everything else in this thing is a galaxy. In fact, in this image alone, they counted 10,000 galaxies. So if this is, of the order of 1/10,000,000th of our observable universe, and there are 10,000 galaxies in this, you can do the arithmetic and you get 100 billion galaxies. And these galaxies are things like this. This is M81, so this is a nice spiral galaxy, very much like our own Milky Way galaxy. And in a typical galaxy of this size, or the size of our Milky Way, is of the order of 100 to 400 billion stars. Okay, so you do a little bit of arithmetic here. You have a galaxy has 100 billion stars, and then you have 100 billion of those galaxies, and so you get numbers in excess of 10 to the 22. And I know Google is, 10 to 100, so it's a very large number of ordinary stars, because most stars are like the sun. Main sequence stars are very much like our own planet. I like to show this image because this is two colliding galaxies. So here are two galaxies of 100 billion stars, and they're actually literally passing through each other. In this collision, no stars will collide. It is purely a gravitational effect, and they will distort and alter each other as they pass through. But the result of this collision will be the stimulation and the birth of stars out of the gas and dust, which makes up most of a galaxy. Because remember that only about 0.5% of the 4.5% is in the form of stars. The rest of it is in gas and dust that's in between the stars. So with these huge number of stars out there, the question is, well, how many solar systems are out there? And when you went to school, or at least when I went to school, there were 9 planets. And then suddenly we went to 8 planets. And so we're saying, well, gee, that's going in the wrong way. Today, we have now thousands of observed planets around other stars. This was one of the first objects of the first observation of a compact object around a star. So here's the star, and this is actually a brown dwarf here. This is taken by the Hubble Space Telescope, and this was in 1995. So this is the first time we were ever able to resolve an object in orbit around a star. And it was also the time in which Jeff Marcier up in the Bay Area and his team used what's called the radial technique, looking for a wobble in a star because something is in orbit around it. So with this radial technique, they were able to identify planetary systems. Today we have another technique by which we look for potential planets around other stars, and that's what's called the transiting technique. This is you're staring at the star and a planet comes along, and as the planet passes in front of the star, the planet being dark, the star being luminous, is you get a dip in the brightness of the star. And this repeats with every orbital period of the planet. So it's a very well-established signature. And so by using this technique, we can identify other stars. And the great thing about this technique is not only do you detect the star and its period, you also get an idea of how big this planet is, relative to how deep this occultation occurs. Now, in the case of the sun, this is and our own planet Earth, this is a very small effect, about 10 to the minus 4. So there's actually an opportunity for everyone here to participate in the observation of a transit. This is a simulation. On June 6 at 0000 UTC is when the simulation demonstrates. The planet Venus is going to pass in front of the disk of our sun. And so this is how big Venus appears on our solar disk, and Venus is very close to the Earth in size. So with a pair of safety glasses, ones that are designed for being able to stare at the sun, you too can observe this. It'll probably be visible via the naked eye through the filter. but a pair of binoculars or a telescope with a solar filter, and we'll clearly be able to resolve this. It'll take several hours. Here in Southern California, the transit will start about 3 p.m. local time, and it will last until sunset. So you'll get about 4 or 5 hours of observing that transit. But it is a difficult measurement to make, because this is a picture of the sun taken through a solar filter. This is one I took with my digital camera, and this is of the transit of Mercury. That's a sunspot right there. But if you look at that little dot there, that's the planet Mercury, as seen from the Earth. So you can get an appreciation for how challenging this measurement is. And you have to account for variations due to sunspots and stellar instability. So what NASA has done is we've put a spacecraft in orbit called Kepler. And Kepler's job is to stare at a region of the sky. So here is, you can see the band of the Milky Way here. Here's the constellation Cygnus. Here is the field of view of the Kepler telescope. It's a 91 megapixel focal plane array. And it's just going to stare at that one place in the sky. It's about 10 by 10 degrees on the sky. And it's going to stare, it is staring at that, and it's just looking for blinks in a collection of about 150,000 stars. So it's looking at all these stars simultaneously, looking for those subtle signatures. So this is some early data. So this is just a cartoon of the focal plane array. And these colored dots are all the planetary candidates that Kepler has found. And the number is now in the thousands that Kepler has found on just this one set of stars that it's been staring at simultaneously. And you can see here there are many, many Earth candidates. So using this data and others, there are now estimates as to how many stars have planetary systems. And right now, the average is, based on one set of analyses, is there's 1.6 planets per star in our galaxy. 1.6 planets per star, meaning that practically all stars have planets. So clearly there's some that have multiple planetary systems. Kepler has seen several candidates where you have multiple planetary systems. And now the estimates are how many of them have Earth-like planets, small, rocky planets like the Earth. And I did an estimate based on some of the Kepler data, and I came up with that 3/4 of stars have Earth-like planets, or at least there's the rate of Earth-like planet occurrence is about 0.75 Earths per star in our galaxy. And now you can extrapolate that to say, okay, well, the laws of physics in our galaxy are the same as the laws of physics in other galaxies, as we understand things. And so it's reasonable to say that other galaxies form the same way our galaxy formed, other stars form the same way, and so planetary systems form the same way. And so you could expect that other galaxies have the same kind of occurrence of solar systems of planets. So we'll go back to that 10 to the 22 number of stars in the observable universe, multiplied by 1.6, and you get a very large number of planets. Multiplied by 0.75 to get the number of Earths out there. So there's a huge number of candidates in the observable universe. So we are very much in a universe that there are numerous planets. So we're at the point where there are now more planets, or the estimates are there are more planets than there are stars. Okay, so what we're interested in are things that look like this. I want to draw your attention to this little dot right there. That's the Earth seen from deep space. This is the Earth taken by the Voyager 1 spacecraft back in 1996 as Voyager 1 left our solar system, looking back. And it just shows how insignificant we are. Again, you know, we thought we were the center of the universe. That wasn't true. So now we're clinging to the notion that, well, we're special because we're the only place that has life. And so the question now is that really true? With so many potential Earth-like candidates in the observable universe now, what is the probability that we're really special? Well, let's come back to our own solar system and ask the question about life in our own solar system. So back in 2006, this is a comet not seen in the southern hemisphere, this spectacular object. Comets are of great interest because our analyses have shown that they have organic materials. The theory is that the water here on Earth was brought to this planet by comets bombarding and leaving behind their icy payloads. In 2005, NASA had a spacecraft called Deep Impact. We sent it towards a comet. This is Comet Temple. And what we did is we carried a little impactor with that spacecraft. So as we flew by the comet, we released this impactor. It then slammed in at hypervelocities into the comet, making this great explosion. And by studying the plasma, the ejecta, the spectra of the emitted signature from this, it gave us an idea of what comets are made of, how they're constructed, what is the inventory of material. And yes, in fact, they are these big icy balls that carry a tremendous amount of liquid water and trace amounts of organics. But one question is, were comets the seeds that brought life here to the Earth? Did life originate on the Earth? Is it special and unique to the Earth? Or is it common elsewhere? Is it carried elsewhere? And even if life started here, could it start somewhere else? So these are questions we want to try to answer by examining other places in our solar system. So if we stop by Saturn on our cruise through the outer solar system, you can see the on-edge plane of the rings. And this is Titan, the largest moon in the solar system. Titan is larger than the planet Mercury. It's so large it supports its own atmosphere. You can see here this brown, smoggy atmosphere. But it's mostly methane and nitrogen. And there's dynamic processes at work in the atmosphere, things like lightning and certainly circulation patterns. And so you expect that there are very complex organic molecules that are being manufactured out of the basic materials of methane and nitrogen. We have the Cassini mission in orbit around Saturn, and it does flybys of Titan and uses its radar to look down at the surface. And this is a radar map of Titan, and you see flow channels here, and you can see a shoreline to a lake. But this is not a lake of water. This is a lake of liquid methane. So it's very cold there, of course. But it doesn't preclude that Titan is producing very complex organic molecules. And at this point, we can only imagine the range of molecular chemistry that's ongoing right now on Titan. But Titan's not alone in this distinction. Again, at Saturn, another moon. This is Enceladus here, seen just above the ring plane. And when Cassini did an image of Enceladus backlit by the sun, it saw these geysers spewing out, emitting out liquid water. So this is actually the first observational evidence of liquid water someplace other than the Earth. I mean, we know there's water elsewhere in the solar system and in the universe, but it's either thought to have been a vapor or an ice. This is the first direct evidence of liquid water. It's liquid because Enceladus is influenced by the large gravitational field of Saturn, so its interior is wrenched by these tidal forces that keep it liquid, and they erupt as geysers. But what this tells you is that you have liquid water. You have a source of energy from this tidal energy, so you're not dependent on solar energy that could drive a potential ecosystem on Enceladus. So this would be an exciting target. So this is potentially a habitable environment within our solar system. If we move on to Jupiter, this is a picture taken by Voyager spacecraft, so back in the 80s. And you have the moons Io, Europa, and Callisto down here. And if we take a closer look at Europa, we see that it's an ice-covered world, and it's fractured and broken. And looking more closely at the ice, it's actually floating. These icebergs, if you will, are moving about on the surface. There's a liquid ocean underneath that ice-covered surface of Europa. They say that this is the first ocean to be discovered since Balboa stared on the Pacific Ocean many, many centuries ago. But this is also significant because it is liquid water. It's liquid because Europa is influenced by Jupiter's gravitational field, so there are tidal forces there as well that are keeping this water liquid, keeping it warm, warm in a relative sense, and providing an energy source that could drive a potential ecosystem. From other measurements, we know that this liquid is briny, it's salty, because it exhibits some level of conductivity. But once again, who knows what exists underneath this ice pack, you have an environment that supports liquid water with an energy source. And the fact that we know that there are organics around, because Jupiter certainly has nitrogen in its atmosphere. I mentioned for Titan at Saturn. And so it's reasonable to estimate that there are inventories of organic molecules or compounds here as well. So you have these pieces that all lead together for a habitable world in our own solar system. Now, where I've been spending most of my time for the last several years is exploring this world, the planet Mars. And Mars, of all the places in the solar system, is the one that's most Earth-like. This is a ground-based telescopic image of the planet. So this is how the world knew the planet Mars until the dawn of the space program. But what you could see is that Mars has a polar cap, has two polar caps. It's tilted on its axis by 25 degrees, very close to the Earth's 23 degrees, which means that Mars has 4 distinct seasons just like the Earth. A Martian year is almost 2 Earth years in length. And over the course of the Martian seasons, these surface features would change, these albedo features. This led Percival Lowell 100 years ago to postulate that there was an advanced civilization on Mars that was planting crops, tending soil, and the changes, as you saw, were foliage changes with the season. He went further to say that they were building canals to bring water from the polar caps down to the parched equatorial regions. But it wasn't until the dawn of the space program that we really got to answer those questions about Mars, about whether it supported a civilization. And this is a picture taken by one of the Viking orbiters in the mid-1970s. And you can see here that Mars is a very barren place. You can see craters just like you find on the moon, but notice they're eroded, they're worn away. So clearly there are processes that have been in play here on Mars. It has an atmosphere, but it's a very thin atmosphere. It's only about 1% of the Earth's atmosphere, and it's mostly carbon dioxide. But the question is, well, what's been going on Mars? And the Viking missions were intended to look for life. They found no evidence, no conclusive evidence. So it was about 20 years before interest resumed in Mars in the exploration. So in the mid-1990s, on a mission that I was part of called Mars Global Surveyor, we started to take a global perspective to studying Mars. And this is some of the data that came from that mission. This is altimetry data. So red and white are high elevation. You can see the volcanoes over here. Blue and purple are very low elevation. And what's striking is that Mars has not only a very low northern hemisphere, but a very smooth northern hemisphere. In fact, it's one of the smoothest surfaces in the solar system. The only area that's smoother than that is the bottom of the ocean here on the Earth. So coupled with its elevation, its smoothness, and these very curious channels, which very look like flow channels, has led some scientists to postulate that Mars had a great northern ocean at one time. Also from Global Surveyor was this image, one of many images, give you a sense of scale. This is about 3 kilometers across the field of view here. This is a canyon system carved by flowing water. They know it's water because they can estimate the density, the viscosity from the topology and geology of this. But what's important here is that this narrow channel down the middle of it, which tells the geologist this was carved by slowly flowing water. Okay, we've always known that there's been water on Mars, actually from the very first days of exploration. But we don't know whether Mars had persistent water up until now. Because the atmospheric pressure on Mars is so low, water can't exist as a liquid. You remember your phase diagram from high school chemistry? Below a certain atmospheric pressure, water is no longer a liquid. It's either an ice or a vapor. Well, that's where we are on Mars today. So the fact that we see that liquid water existed on Mars and existed for an extended period of time, because this canyon system doesn't form overnight. It takes hundreds of thousands of years to tens of millions of years to make a feature like this. And so liquid water persisted on Mars for that kind of time scale. And so here we now have tantalizing clues that Mars must have had a habitable environment. Because you had liquid water, you had persistent liquid water. The fact that it was liquid means that Mars has to be warmer, the surface temperature has to be warmer than it is today, and you had to have a thicker atmosphere than it is today, something that is more Earth-like. Well, the way to answer some of these questions is to go back down to the surface with the Mars Exploration Rover. And this is one of the 2 rovers that's part of my project, Spirit and Opportunity. And this is a picture taken of the rover at JPL while it was being developed. And so you can get an idea of the size of this vehicle. It's 6-wheel drive, so each wheel is independently driven. We have small motors in each wheel. The 2 front wheels and the 2 rear wheels independently turn. It's solar powered, so we have these deployable solar arrays, so there's no consumable. As long as we can get sunlight, we can power the rover. It carries everything with it. It has its communication antennas here that can communicate directly to Earth or with orbiting spacecraft. This white mass supports a set of cameras up here, and you notice the cameras are pretty much at human height, so the images it takes have very much a human perspective. There's another pair of cameras down here in front, another pair in the back. And these cameras are in stereo pairs, so the rover sees like the way you and I see, stereoptically. It has depth perception, so the data that we take is inherently 3-dimensional, and the rover uses that to navigate and operate on the surface. There's also a robotic arm here, tucked up underneath, about the size of your own arm. And it has a set of devices on the end. One is a rock grinder, which is like the geologist's rock hammer. And another is a microscopic imager, which is like a little magnifying glass. And what we are doing and have been doing for over 8 years now on Mars is classic field geology with these rovers. So here's where we went, and here's where we are with the rovers. The first rover, Spirit, landed in Gusev crater. So this is a crater that's about 160 kilometers in diameter. This is our entry ellipse, our bullseye on the surface. We chose this because we see from orbit evidence of a great flood channel. There's a great river. You can even see the remnant of the river delta here. You can see where the water breached here to the north and flowed away. So there's evidence that this one time was ponded with water. So we're expecting to find sedimentary material here. Almost completely on the other side of the planet is where Opportunity went, and that's shown here with this coloring that's laid on top of the image. And that coloring corresponds to the presence of a mineral called hematite. Hematite is an iron oxide. You might know it as the silver gray jewelry. It forms in an aqueous environment. So this is chemical evidence that there was water here on Mars. And this is the only place on Mars where we see this signature from orbit. So we have visual evidence and chemical evidence of water playing a role at these 2 sites. And so that's where we've sent our rovers. So here's a picture taken by Spirit after landing. You can see this is what's left of our lander on the surface with the airbags that brought us safely down. And you can see the rover has been driving. Now, these rovers were designed for 90 days of exploration and a traverse capability of about 1 kilometer. So the time was ticking, and we went on exploring these rocks, and what we discovered is all these rocks are volcanic. Now, this is Gusev crater. We were expecting to find sedimentary deposits, evidence of ancient water, and all we were finding is volcanism. So that was kind of a monkey wrench in our exploration. Opportunity on the other side, here's where Opportunity landed. This is a small crater, just a little crater called Eagle. And here's our lander system. And you can see the exposed bedrock here. And you can see where the rover has been exploring that. And here, the rover hit a hole-in-one right from the get-go. As we went up to these rocks, you can see the wheel tracks here. And no, that's not a boot print. That's the wheel track. You can see the laminations in the rock. These are sedimentary rocks. These were laid down in water. So this was the aha moment. This is evidence that the bedrock of Mars contains direct evidence that at one time there was liquid water here. These rocks formed in water. They don't form overnight. So water was persistent on geologic time scales, surface water on ancient Mars. How long ago? Well, the best we can estimate right now is somewhere around 3.5 to 4 billion years ago. Now, on Earth, 3.5 to 4 billion years ago, life was just starting. So we know at that time, in that epoch, there were at least 2 places in our solar system that were Earth-like. The Earth, where life started, and Mars, which exhibited many of the same Earth-like features: liquid water, warm temperatures, thicker atmosphere. So life started on Earth. Why not Mars? And even if life started on one or the other planet, we know from meteor analysis that the 2 planets have exchanged material over time. So the question is, was there life on Mars? Can we find evidence of past life? Is there life there today? Well, these rovers are don't have life detection capability. It's a geology mission, and that's what we've been doing. You can even see where we've ground into the rock here, and we've measured the geology. And this water, this ancient water, was not only liquid, of course, but it was salty, it was acidic, and it was evaporating. Here's a rock that we found, and it's not a Martian rock. This is a meteorite. This is a rock from somewhere else that landed on Mars. It's a stony iron meteorite, and you can see the characteristic fusion crust. So this is further evidence of not only the exchange of material between the planets, but also that Mars had to have had a thicker atmosphere, because you wouldn't find a rock like this lying on the surface. That a meteor would have just ended its entry in a huge crater on the planet. So this probably had a very glancing angle when it hit the planet, but there must have been a thicker atmosphere, not only to create the fusion crust, but to land this meteorite onto the surface of Mars. So further evidence of this notion that Mars had a thicker atmosphere and then was more Earth-like. Well, the rovers lasted their 90 days. Spirit actually went on to last for over 6 years. Opportunity is still going at over 8 years. But because these rovers last longer, we're able to drive them. At this point, we're able to drive Spirit several kilometers to a set of hills. And climbing up the hills, this is where Spirit found the first evidence of watered, altered rocks here. So this rover as well has found evidence of ancient water on Mars. But one of the other significant discoveries that Spirit made is this outcrop here, which turns out to be made of somewhere between 30 and 40% weight carbonates, calcium carbonates. And this is a big deal. Because if Mars lost its atmosphere, the question is, where did it go? Well, one theory is that it was a carbon dioxide atmosphere, and that over time that atmosphere became geologically sequestered in the surface materials. That happens here on the Earth. It happened on ancient Earth. But we have these things called subduction zones and volcanoes, which tend to break that stuff down and put it back into the atmosphere so it's accessible to living things like you and me. But on Mars, there are no such processes. And so one theory is that we would find evidence of an ancient atmosphere in the geology of Mars. This is not conclusive, but it is compelling as to what might have happened to the atmosphere on Mars. Oh, by the way, it also requires that you have liquid water for the CO2 to dissolve and then to eventually get mineralized. So it's further evidence of not only the atmosphere, but abundant liquid water on the surface. Well, we've been driving Opportunity, and you can see the distances we've traveled. We came across another highly eroded crater, and once again we found evidence of sedimentary rocks. But this is a little bit different. Notice these laminations are not parallel, they're wavy. These are rocks that were formed in a dynamic environment. This is either an ancient shoreline or an ancient stream bed. So now we have even more compelling evidence of the Earth-like characteristics of ancient Mars. Now, after about 2 years on the planet, we had a failure in one of the wheels on Spirit. Again, these rovers were designed for 3 months and 0.6 of a mile driving. At this point, we'd driven Opportunity Spirit about 4.5 miles, and one of the wheels failed. And as a result of the wheel failing, it doesn't freely spin because it's got a large gear reduction on it. And so we drive with the remaining 5 wheels, so we drag that one wheel like a ball and chain. But there's a benefit to that. There's a significant scientific benefit because it tends to scrape up what's just beneath the surface. And this is something we would have just driven right by. We would never have noticed it. This light tone material you see here is amorphous silica. Basically silicon dioxide in an opaline or hydrated form. But this is evidence of a precipitate out of a hot aqueous environment. So this is evidence of an ancient hydrothermal system, something like a geyser, a hot spring, or even a deep ocean vent. We know here on Earth that those hot springs or those geysers or even the deep ocean vents are thriving ecosystems because not only do you have liquid water, but you have an energy source that can drive that ecosystem. So this is evidence that there were energy sources on the surface of Mars that could further drive a potential ecosystem. Well, Spirit had 2 of her wheels fail, and she became embedded in this loose, fine material you see here. This is the robotic arm in the front of the rover. And this is where Spirit came to rest. And we've since lost communication with the rover because we weren't able to position it for the winter. But even in their last act on Mars, she made yet another discovery, this loose material, and you can see the variation in colors and textures. These are unconsolidated sulfate minerals, hydrated sulfate minerals. This is evidence of more recent water action on Mars, something maybe of the order of 1 million years ago. So not ancient water, more recent water on Mars. So again, this is tantalizing bits of information. And there's even arguments there's liquid water on Mars today. So still this compelling question about ancient life on Mars or even current life on Mars. Opportunity is still driving, and I wanted to give you this map. This is where we landed in Eagle Crater. This is one of the large craters in Durance we explored. And then we drove several kilometers down to this huge crater down here, Victoria. This is about a half mile in diameter. And we've driven about 12 kilometers to this point, so 12 times farther than it was designed to go. And we like exploring craters because they're holes in the ground. They're like time tunnels because it's the rocks at the bottom of a crater are older than the rocks at the top of a crater. So by going down into a crater, you're going back in time. So we're reading the chapters of the Martian history book in sequence. But we spent about 2 years exploring around Victoria Crater, and we wanted to say, okay, well, what's next for the rover? Because it's still in good health. We can still drive this thing. So just keep this distance in mind. And as I go to the next slide, that's this distance here. This is where we landed, and here's Victoria Crater. We have since, over the intervening 3 years, driven Opportunity over to this giant crater. And so we are now at 34 kilometers of odometry, more than doubling the remarkable 12 kilometers to here. And we are here because this rim material, you can see this is an ancient crater. It's highly eroded. It's giant in size, of course. But what we see in the rim of the crater from orbit, from one of the orbiting missions, is the evidence of clay minerals. And this is yet another piece to the story about ancient Mars, because clay minerals are minerals that form in water, and they tend to form in a neutral pH environment, a neutral aqueous environment. Further, clay minerals have this tendency to preserve what was ever in the water when they formed. So here's the question. If there were ancient organic molecules, if there were organic molecules on ancient Mars, they would probably not be around today because the ultraviolet radiation from the sun that sterilizes the surface would have broken down any of the organics that might be present on the surface. However, they may be sequestered and protected inside of minerals like these clays. So these represent a potential time capsule to explore. And so this is where Opportunity is today. Here's a photograph showing the rim of this giant crater. You can see it appears like a mountain range. We're in wintertime right now. Actually, Friday is the winter solstice on Mars for Opportunity. So we have the rover stationary right now because of limited energy, but as soon as the spring season comes, we'll be again driving, and we'll be going and exploring these hills, looking for these clay minerals and seeing what clues they hold about ancient Mars. But one of the more recent discoveries is this vein of light material. This is gypsum. Gypsum is a hydrated sulfate. So, and this is gypsum that formed here. So we know at this spot there was liquid water. It wasn't formed somewhere else and the minerals were transported here or whatever. We know for a fact now that there was liquid water percolating up through this fracture in the rocks, forming this gypsum that survives there today. Opportunity, though, is fairly challenged right now. This is a self-portrait of just taken about 2 months ago. Much like, when we update our Facebook page, our Google Plus page, we hold out our cell phones at arm's length, take our picture. Well, we did that with a camera on the mast, and you can see it's a mosaic of several hundred images. But you can see how dusty the solar rays are. When this picture is taken, about 50% of the light is obscured by the dust on the solar rays. And you can see we're almost camouflaged against the background. We have experienced some dust cleaning events from the wind. Seasonally, as we move into the spring, there have been occurrences of these dust cleaning events. In the past, they've done a pretty good job of cleaning the rover off. So, and that's really the explanation for why the rovers have lasted so long, because the dust was what we thought would limit the life of the rovers. The dust cleaning allowed them to be able to survive the winter. But Opportunity will begin her exploration of further along the rim of Endeavour Crater. But shortly, on August 5th, Opportunity will be joined by another rover, and that is Curiosity, the Mars Science Laboratory. And this is a much bigger rover. You can see here how large this vehicle is. The wheels are twice the diameter of the wheels on Opportunity. It's 5 times the mass of Opportunity. So this is almost over 900 kilograms of mass. This rover is going to be nuclear powered. It'll have a radioisotope thermoelectric generator, a nuclear battery, so it won't have the complexities of solar arrays. But a larger rover, a bigger rover, can carry a lot more instrumentation. This carries over 100 kilograms of instrumentation, 10 times what Opportunity carries. And one of the important instruments on this is called SAM, which stands for Surface Analysis at Mars. It's a mass spectrometer. And it has the ability to detect not only elemental and isotopic compositions throughout the periodic table, but it also has the ability to detect organic compounds up to about 400 Daltons, 400 atomic mass units. So it can look for complex organics. It can actually uniquely identify amino acids or nucleic bases. So if there are organics on Mars, and it has a very large robotic arm on the front with a drill that it can take core samples from beneath the surface, only a few centimeters down, but deep enough to where things might be protected from the ultraviolet radiation. And it can extract those samples and introduce them into the instrumentation, which is in the belly of the rover, and look for the presence of these complex organics. And so that would be a very exciting discovery, because we know geologically that Mars was a habitable world. It had liquid water, it had warm temperatures, it had energy, sources of energy to support an ecosystem. The next question is there the inventory of organics that could be the building blocks for life? Now, this is not a life detection mission. We would only be able to detect whether there are the building blocks to support a biological system. It'll take future missions, perhaps a sample return mission, to answer the questions about Mars. The exploration of Mars continues. This is sunset on Mars, seen by Opportunity. You can see the sun is smaller because we're further from the sun. And on Mars, the sunsets are backwards. Mars has a pink sky and blue sunsets, where on Earth we have a blue sky and pink sunsets. But this goes back to the earlier question is, are we alone? We have seen in our own solar system that there are several places where there are habitable environments, whether it's Titan, Europa, Callisto, the planet Mars, and the Earth. And then we know that there are numerous planets out there in the observable, an incountable number of planets. In fact, there are more planetary candidates in the observable universe than there are grains of sand of all the beaches here on Earth. And that we know that in our own solar system there are several places where habitable environments exist. So the question is, how special is this place here? Are we alone, or do we share the universe with others? And the other great question, in addition to searching for life, is what happened to Mars? How did it lose its atmosphere? What happened to its liquid water? What changed on Mars? And can it happen to the Earth? And is it happening today? To be good stewards of our own planet, we need to understand how planets evolve and change. And studying other worlds like Mars and the other planets helps us to understand our own world. And so we can make the right decisions for ourselves on this world. So I will end here. That you can find all these images at the JPL website. The adventure continues, and I hope that you will follow along as we continue this great exploration and addressing these questions. Thank you very much. Thank you. Thank you. Thank you. I think we have some time for a few questions. So, yes, in the back.
Let me give you the microphone.
Okay, great. Some people think that the Viking actually might have discovered life in '76, but we weren't looking for the right kind of life. Do you have any opinions on that?
Well, I'll tell you that there were each Viking lander had 3 experiments and 3 control experiments. And they found in one of the experiments a signature. And the question is that due to something living, or was it due to another reaction? The conventional explanation for that signature was that it was due to a peroxide interaction in the Martian soil. But it's compelling but not conclusive. And so today we have a better understanding of what life is like, and we also have an understanding that there are extremophiles, life forms here on Earth that can live in extreme environments. So people are revisiting that question. I think the general consensus is that Viking did not find evidence of life, but it's by no means closed the door on that question. Other questions? Yes?
What's your take on the Fermi paradox? Why haven't we seen any signals of life from elsewhere?
Let's see. First of all, there's a lot of space in space. There's a lot of distance between the other worlds. So, and the other part of it is we're just beginning to open our eyes to seeing these things. You know, in the case, for example, of planet detection, the first planets we discovered were these very large Jupiter-sized planets that orbited very close to the star. Why? Because those were the easiest to see with the techniques that we're using, the radial technique. Kepler now, using the transiting technique, is finding even more planets. And the planet it's finding are the short period ones, because you have to stare for a period of time and look for the blink. And the shorter the period, the more blinks you get in a fixed amount of time, and so the stronger the signature. As Kepler continues to look, we're finding longer period orbits. So all that is to say that we're just starting to look, and we're very biased in our way that we're looking because our instrumentation isn't sensitive to everything. It's only sensitive to a few things. So as we expand that envelope, the discoveries will flood in. So perhaps that's why we haven't heard or seen anything yet. Yes?
And planets, they're at their axis of rotation. Why are they tilted? What makes the axis tilt?
Okay, well, let's see. First of all, it's all about angular momentum. You know, when planets form around a star, you get material that collapses in, most of it accretes to the center to become the star, but other material forms a disk around the star, and because you need to conserve angular momentum, it forms in a disk, and it stays in orbit, and then the planets form out of that, and so they tend to pick up the angular momentum stored that's part of the disk material, and so they spin. So naturally you would think they would be aligned with the disk plane, but they're not. And part of the reason is that they experience torques. Planets aren't exactly spherical. They're kind of squat and chubby, and that results in a torque being applied by not only the star but other planets, and that torque causes a precession of the spin axis, and so that's why some of them. In the case of Uranus, it's almost completely on its side, and we think that's because Uranus was hit by some other interstellar object that knocked it over.
Would life on Earth be able to survive if the magnetic field is as weak as Mars?
Oh, a great question about the magnetic field. You and I are here today because we have a magnetic field here on the Earth. The magnetic field creates a bubble that protects our atmosphere from the ravages of the solar wind. Because without a magnetic field, you can literally blow the atmosphere off a planet, much like blowing the seed pods off a dandelion. And that's one of the theories of what happened to Mars. Mars is a smaller planet. It did have a magnetic field at one time, but perhaps its core solidified, freezing out the magnetic field. Losing the magnetic field, the solar wind blew some or all of the atmosphere off the planet. And of course, being a smaller planet means that the atmosphere is less gravitationally bound. Without that atmosphere, the liquid water is broken down by ultraviolet radiation to hydrogen and oxygen. Hydrogen drifts into space. The oxygen oxidizes surface materials, and that's how we end up with Mars today. So we should all be appreciative that we have a magnetic field here on the Earth. So the question is, could life survive without it? Well, you're more subject to solar wind radiation in that instance. Yes, up here in front.
So it seems to me that the building blocks that we've identified, water, organic compounds, a source of energy, may be abundant. But I'm not convinced that the genesis of life, it seems like it has to be a very improbable event. And since we haven't seen any intelligent life, it must be so improbable that, you know, it's hard to fathom how improbable. So it may be that it's actually compensating for the size of the universe. Maybe there's only an expectation one other life form, or maybe none. You know.
You raise an excellent point. We don't have that information yet. We haven't found life elsewhere. Some people argue that life could be abundant. That the transition from a non-living environment to a living environment could actually readily occur. We found here on Earth that you can form complex organic molecules in a variety of environments, but how do you make the leap from amino acid to living system? We don't have the answers to that yet, and so you're absolutely right. It could be that maybe we are still special in some way, but we don't know. I will just caution that we really are just beginning to peel back the layers of the onion as we look to the outer these outer worlds, and as missions like Kepler and others start just revealing the incountable number of worlds out there that have habitable environments or potentially habitable environments, you start to run into some pretty tough mathematics as to the possibility. So even though the possibility is really low, because we know it happened at least once. So you start you don't have to have a very high batting average if you get 10 to the 22.
Perfect principle. That's like a sampling bias. We wouldn't be around to say, oh, why didn't we exist if we hadn't?
Those are excellent points, and that's part of the discussion, debate, and exploration that's ongoing right now.
So I want to put you on the spot. What do you think is perhaps the number, if you had to guess, of life forms in the universe?
I have no idea. I only know about what's here on this planet. So,
so you're not going to get.
I higher planets.
Okay. Well, how about we take? I'll gladly stay around for more questions, but I know some of you need to get back to your office, so we'll take one more question.
Okay. So, if there were, say, a planet 10 light years away with the same outgoing radio transmissions as Earth, would our equipment here even be sensitive enough to detect that?
I think the answer is yes. You know about SETI, the Search for Extraterrestrial Intelligence. They have had a campaign for decades now looking for that signal, and that the argument being is that if someone has the kind of communication technology that we have, that it should be detectable on interstellar distance scales. And so, yes. And then we would know, and then we could ask them whether they have Google there too, and go from there. Okay.
Okay.
Well, one more question then. Great.
Just a quick follow-up. So what then would be the limit of the detectability with the strongest, clearest signals that we can transmit? How far away could we detect? If 10 light years we can detect, 100 light years, how far?
I don't know the answer to that, but what we are trying to do is see if we can detect the spectral signatures in these planetary candidates that we find that are 10 to 20 light years away. See whether we can. We already have the ability to detect the atmospheres on some of these worlds through very exciting techniques. But what we want to do is we want to look for essentially chemistry out of equilibrium. We want to look for abundant oxygen or ozone. We want to look for the presence of water and methane. If we see a planet, if we could resolve a planet and we see the spectral signatures for oxygen and water and carbon dioxide and methane, there's a pretty good chance that something is making that chemistry out of equilibrium. Because here on Earth, we have an oxygen atmosphere because we all have this, all this damn life that keeps producing oxygen all the time and fills the atmosphere with it. Otherwise, the oxygen would have combined with the surface geology. So if we find oxygen as one, it starts to become a strong argument that there's something going on there that's out of the ordinary. And we feel that today we're close to having that ability to go out 10 or 20 light years on things. Well, thank you again for having me. I hope you've enjoyed the time together.
Thank you, John.
Thank you. On things.